Okay, so let's look at what can happen when we're solving these simultaneous equations or matrices. Now, we'll start with two dimensions because two dimensions is nice and easy and we're all sort of used to it. And we also always think that if you've got two lines, they intersect at one point, which is 99% of the time true. If you've got y equals x plus 6 and you've got y equals 2x minus 3, they're at different gradients and they're two very simple lines or graphs of that. But we know at some point, because they're at different gradients, they are going to intersect at a point. And that often happens. Other things that can happen is when you've been asked to solve simultaneously y equals 2x minus 1 and y equals 2x plus 2. Now, we can see straight away, because of the 2x, that these lines are parallel. Because they're parallel, they'll never meet. Therefore, here we have no solutions. We don't have any solutions here. The other case that can happen is that you have two lines like this, y equals 2x plus 6 and 2x minus y plus 6 equals 0. And if you were to graph those two lines, what you would find is that they're actually the same line. We could just move the y over and it becomes y equals 2x plus 6. Now, in two dimensions, because we're more used to that, we can notice that straight away. Let's see what happens in three dimensions, because obviously it can happen in three dimensions. Weird things can happen when we're solving these. So let's have a look at this. We've got three sets of equations, three unknowns. That should be enough to solve this problem. We've got x plus y equals 10, x plus y plus z equals 10, 2x plus y plus z equals 13, 3x plus 2y plus 2z equals 23. And I've drawn the little matrix there. Now, again, let's use that same sort of notation. We're going to let R2 become R2 minus 2 lots of R1. And we're going to do R3 is going to become R3 minus 3 lots of R1. Okay, so how do we get that? 2 lots of this, or 2 minus 2 lots of this, is going to give us a 0. 3 minus 3 lots of this is going to give us a 0. I've tried to keep the numbers fairly simple. Again, we have not touched the top row, so we can just leave that. The second row is going to become R2 minus 2 lots of this. That's our formula here. R2 minus 2 lots of R1. So 2 minus 2 lots of this is 0, exactly what we want. 2 minus 1, this minus 2 lots of this. You've got to be really careful, and I'm sometimes stuff up. 1 minus 2 lots of this is going to be minus 1. 1 minus 2 lots of this is going to give minus 1. 13 minus 2 lots of this, which is 20. 13 minus 20 is minus 7. Exactly the same here. Row 3 is going to become row 3 minus 3 lots of R1. So row 3 minus 3 lots of this is 0, exactly what we want. 2 minus 3 lots of this. 2 minus 3 lots of this is minus 1. And again, 2 minus 3 lots of this. 2 minus 3 is minus 1. This minus 3 lots of this. 27 minus 3 lots of 10 is 30. 23 minus 30 is minus 7. Now, obviously, these two rows are exactly the same, and therefore we can't solve this because the three variables are not independent. So that's one of the things that can happen, that just because we have three equations in three unknowns, it doesn't mean we can solve it, because if you look at this, the third equation here is not really a new equation. It is dependent on these three in that sense that x plus 2x is 3x, y plus y is 2y, z plus z equals 2z. So it's not giving us, and 10 plus 13 equals 23. It's not giving us any real information. This equation is not independent of the other two. It is some form of those other two combined. The other thing, of course, that can happen is if this was, instead of 23, it was 0, then this would have obviously been 0, and this would have been 0. And then you've got even worse things happening, because here it's saying that minus x minus y equals -7, and minus x minus y equals 0. And that's when you have some sort of, you don't even get an answer. But Alan will talk about that in terms of vectors, and what that means in terms of vectors, that two of the vectors are on the same plane, and things like that. Okay, thanks.